Hello students and welcome to another video. I'm your teacher, Mr. Flynn, and today we're going to be talking about acids and bases. Now, when we talk about acids and bases, what we're referring to is the concentration of hydrogen ions, and in bases, we're talking about hydroxide ions. Now, the unique thing about these is when you put them together, we form water. So what we're doing is we're examining the concentrations of the different parts that make water. That's really what acids and bases is all about. Okay, now for example, in this let's go through this. Let's talk about some characteristics of acids and bases. So acids back in the past, all right, how we used to identify them was when they tasted sour. Now examples of acids that you may be familiar with are like lemons or vinegar, all right, and they taste sour. Now bases tend to taste bitter. Okay, and examples of bases are like soap or baking soda, right? And so that's how they used to identify acids and bases in the past, all right? Now, when we're like talking about how they feel, okay, bases are really slippery, okay? Like soap, all right? It's a good example of this, okay? Soap has a lot of hydroxide ions in it. Okay, now acids aren't necessarily slippery, but they react with metals. Okay, right, and that's what this picture right here in the corner is for our advanced topics, is basically an acid etching away at the surface of metal. Okay, and so before we understood what the chemistry of acids and bases were, people in ancient times actually used to recognize the properties of them by what we were able to observe. All right, so if they were sour and they reacted with metals, you're probably working with an acid. Okay, if they were bitter and slippery, all right, they would be saying, oh, I'm working with a base. All right. Okay, and when we're talking about like the pH scale, okay, 7 is what sits in the middle between acids and bases, and it runs from 0 to 14. So any value less than 7 that runs to 0 is an acid, and it gets stronger as it gets closer to 0. Bases run between 7 and 14, and they become more basic as they get toward 14. So you can almost draw it like this, like they become increasingly more and more and more basic, more and more and more acidic, like this. Now, basically at 7, you're working with something like water. And then if it's neutral, if it's just pure water, you're working with a value of 7. And then if you're working with a pH, okay, the powers of hydrogen, less than 7, you're going to be working with an acid, and if it's higher than 7 to 14, you're working with a base. And that's as far as I'm going to take it in this video. Down below, in a separate video, I'm going to be talking about these values and how we calculate them. But in this video, this is really just an overview. So if you see, like, for example, that a lemon, okay, I don't know, I can't remember the value of a lemon. I think it's like a pH of 2, right? Then we can assume that that is going to be acidic, all right? If you're working with something like bleach and it has a pH of 10 or 11 or 12, okay, you're working with something that's basic, all right? And we're using this 0 to 14 scale to measure the acidity and basicness of something, okay? Now, if something had a pH of 6, it's just barely acidic, while something with a pH of 2 is strongly acidic, okay? A pH of like 8 or 9, basically what most drinking water is, okay, is not very basic. But if we have a pH of 10, it's much more basic than just a pH of 8. So 7 is neutral, and then it just kind of swings out either direction, and it becomes increasingly more all the way until 14. Okay? Because if you think about it, if I have a pH of 2 and a pH of 10 and I mix them together, they come together to form a solution. They will neutralize each other and work out to be something like 7 or 8. Okay? It's going to be somewhere in that range. Okay? So acids and bases interact with each other to form water. Okay, and specifically salts. Okay, all right. Let me erase a lot of this. This is just a lot of side conversations. Okay, good stuff to know. All right, as we go through this, just general information. I will keep the top up there. Okay, now when we're examining this, all right, hydrochloric acid. Okay, we're focusing on hydrogen ions. Okay. And what we're doing here is adding a strong acid. So when we say strong acid, what's going on here is that it completely dissociates. Okay, you won't have any H's and Cl sticking together. They will always dissociate. So this H and Cl will separate, and then we're left with, okay, chlorine, which will be dissolved in solution, okay? And then we will have what we form a hydronium ion. And what we're showing here is that there's an extra hydrogen attached to a water molecule, okay? So basically, this hydrogen is going to attach to a water molecule right there. Okay, now, I know it can be a little confusing. Like, well, Mr. Flynn, you keep saying a hydrogen ion. What, shouldn't it just be by itself? Well, it doesn't exist by itself. It's very reactive, and it's going to stick onto a water molecule. But it easily breaks off of that water molecule, okay? So when we're talking about hydrogens or hydronium, they're basically the same idea, okay? But what's really happening is that hydrogen's sticking to a water molecule, but it easily breaks off and can go interact with things. Like, for example, right here, we have a water molecule with hydrogen stuck to it, and it's interacting with the surface. Ooh, I kind of crowded it out. Okay, on this picture in the corner, you can see that this drop here has a bunch of this hydronium ions in it, and those hydrogens are breaking off, and they're interacting with the surface of the metal, that metal surface. Okay? All right, so just keep in mind, all right, hydronium and hydrogen ions are the same thing. Like this hydrogen that I first was talking about, it's the same thing. It's just stuck to water. That's all it is. Okay? Now, hydroxide, if you remember here, we have OH. All right, and it forms sodium hydroxide. That's what this is. Sodium hydroxide is a strong base. So then it always completely dissociates. So the sodium becomes part of the solution. Okay, it stays aqueous. Okay, both of these will be aqueous. The chlorine and sodium will be aqueous. Just like how salt dissolves in water, it's the same thing. And then we have this hydroxide ion that's floating around in solution, and it wants to interact with things. Okay, acids and bases love to interact with things that become part of their solution. Okay, like metals, it will start to etch away. Okay, now a lot of times we're going to use hydroxide ions, okay, to neutralize acids, but we also use them as cleaning products. And the reason we use them as cleaning products is because the hydroxide ion interacts with the membranes of small single-celled organisms like bacteria and breaks them down. So we actually use a lot of hydroxide ions as a disinfectant. And a good example of this is bleach. Okay, bleach is a strong base, and it breaks down the membranes of bacteria. All right, so we found that that's a useful purpose for hydroxides. Okay, all right, now down below, okay, we have a different way that acids and bases are formed. Another way is that the compound can actually interact with the water. So in here, the ammonia, the NH3, is going to take one of these hydrogens off water, and it's going to ionize it and turn it into a hydroxide ion. And when I say ion, it's going to steal, that hydrogen on there, and it's going to turn it into an ion. Okay, and then it forms ammonium. All right, and we've talked about ammonium. If you remember back from our polyatomic ions at the beginning of the year, it's our one positive polyatomic ion. But basically, we could either, what I'm saying is put stuff in water and it separates, or something can actually interact with the water itself and steal those hydrogens right off of it to ionize and form hydroxide ions. Okay? And then lastly, the last thing I want to talk about is self-ionization of water. So every now and then, okay, one of these water molecules will steal one of those hydrogens, and it will form a hydroxide ion and a hydronium ion. But then very quickly, this will go back going that way. So this is really a reversible reaction. What's happening is that hydroxide ion will let it go, and then it will come back. And so basically, water kind of lives in this balance of giving and taking hydrogens. Okay? That's essentially what water is doing. We just don't talk about it like that all the time. But when we're talking about acids and base chemistry, we're going to be looking and saying, yeah, water is self-ionizing. Okay? It's going to be giving and taking those hydrogens off the water molecule. So basically, acid and base chemistry is all centered around the water molecule and how it's giving and taking those hydrogens. Okay. Now down below, there's a really nice chart that I have here. In the other video, I'm going to talk about the math that's associated, okay, with basically hydronium ions and hydroxide ions. But in this video, I want to just focus on pH, all right? When we're focusing on pH, there is a scale, and at 7, it is neutral. Okay, it's right here. Here's our word that I like to use, is neutral, okay? And as we work through this list, you can actually see that as we go from 7 to 0, it's becoming more and more acidic. All right, it's on this logarithmic scale, and it goes by powers of 10. So from 7 to 6, it's times 10 more. And from 7 to 5, it's times 100. And from 7 to 4, it's times 1,000 times more, right? And so as we work our way out, you can see that it's becoming a magnitude bigger. Like for a big step from 7 to 4, we're talking on magnitudes of thousands, and anything past that is tens of thousands and hundreds of thousands, right? And so it accelerates quickly. It's kind of like it shoots up and it shoots down the other direction, right? And it becomes even less concentrated. Okay? Just want you to recognize when we're working with powers of 10, we're not just going up a step, we're going up like by magnitudes of 10. And as human beings, we don't imagine numbers like this, so we have to put them into a scale that's a little more manageable for us. All right, so basically a pH of 2 is hundreds of thousands of times stronger than just regular water versus the ones below it. Okay, and essentially, here's our example. Let's go through a couple of the examples. So here's a lemon, right? It has a pH of 2. It's really acidic, all right, compared to a tomato, which has a pH of 4. All right, and so when you're eating these kinds of foods, very acidic foods, it's good to not basically allow them to touch your teeth, right? Like when you're drinking lemon water, you should have a straw with it, right? Because that acid can actually break down the coating on your teeth, right? Because it's very acidic. Would I worry as much about a tomato? Not necessarily, because it's a higher pH, but it's still acidic, okay? Another example of products is baking soda and bleach. Okay, bleach has a much higher concentration of hydroxide ions, and so it's going to be considered a base, and it's going to be used for cleaning products and breaking down those cell walls, right? And that's the big example from bleach. All right, if you have questions, we can talk more about this. I'm going to make another video about how to do these calculations right here in these other columns, and we're going to work through these math problems here. Okay? All right, thanks again for watching. Until next time.